Hello, and thank you for joining us today on our webinar about how to move faster than AI, outrunning risks through automated security testing. My name's Hayley, and I'm excited to introduce today's session. So I'm excited to introduce our panelists for today. So firstly, we have Devon Jones, who is a solution architect at RunnerX, where she collaborates across product, marketing, partnerships, and more to grow RunnerX as both a product and a brand. With over 10 years of automation engineering experience, including 4 as a lead QA, she brings deep technical and quality assurance expertise. Welcome, Devon. And next, we have John Bronner. John is a software development professional with a passion for .NET and Java technologies. John has always been interested in all aspects of software development. In his 20-year career, he's worked as an infrastructure developer, sales engineer, support director, and he is currently the solution architect for the DevSecOps brands at Sembi. Welcome, John. Great. And just quickly covering off today's agenda. So we'll be beginning with exploring why AI has shifted the security landscape today and the risk areas developers are overlooking. Then we'll be discussing automated security testing frameworks and shifting over to fundamentals from a DevSecOps lens. And of course, finishing with Q&A. Wonderful. And now with that, I'm going to hand over to Devon to kick us off for today. Thanks, Devon.
All right. Okay, so where AI stands today. The rollout of AI technology has been a bit of a roller coaster. We've all acknowledged that while LLMs are powerful, they are not magic and they are far from perfect. The internet is full of examples of AI fails, everything from hilariously warped images to headlines about data theft and security breaches. Over half of the general public and more than half of investors have concerns about the safety and security risks of AI. And half of Americans are more concerned than excited about its future. Basically, the trust in AI hasn't kept up with the speed and depth of its expansion into our everyday lives. So, where are we at with software security in this new age of AI? Few key stats. Almost half of AI generated code contains security flaws, while AI tools now generate almost half of enterprise code. Most organizations use third-party packages that possess critical vulnerabilities. A recent report identified AI generated code as the cause of 1 in 5 security breaches. An analysis of almost 500 GitHub repos showed almost triple the rate of flaws in AI versus human written code. But two of the most concerning data points are that while almost all organizations now use AI code generation, only 12% apply the same security standards to it as they do traditionally developed code, and less than half of developers review AI generated code before committing it. As you can imagine, the cost of this is extremely high. Over 10 million secrets were exposed in public repos in 2025, many linked to automated code generation. The average cost of a data breach reached 4.4 million in 2025. And security breaches tied to AI tools led to longer recovery times, averaging 280 or more days, as per SQ Magazine. So how exactly is this happening? How are the attackers exploiting? What are the vulnerabilities attackers are exploiting that are made more prevalent by AI? Well, the main attack route is prompt injection. Attackers design inputs that cause an LLM to ignore its original instructions, and since it operates on system prompts and user input as a single text stream, it's usually impossible for the model to distinguish between them. This type of attack was successful 50 to 84% of the time. Another common attack was through permission settings. Permission settings, they're one of the top 5 exploit paths, which makes sense, as 33% of cloud-based AI-generated scripts expose privilege escalation pathways. Over 30,000 Chat GPT credentials were discovered in an InfoStealer malware in 2025. Improper use of input and output handling is another common issue. When an LLM takes input or produces output that gets passed straight to another system without verification, This is how AI-assisted code suggestions can lead to SQL injection, as we've discussed already. So what can we do? What can we do to keep our software safe? And this is where we're going to be introducing the topic of security-focused automation. So when we're going through the front end, we can implement fuzz testing, which is basically throwing massive amounts of random, unexpected, and malformed data at your software to see what breaks. Kind of like a hallucination that an AI agent would create. So fuzz testing will automatically generate large amounts of invalid, unexpected, or random inputs, feed them into your application, and then monitor for crashes, hangs, errors, or security vulnerabilities. This type of testing can catch buffer overflows, injection attacks such as SQL or command injection, input validation failures, edge cases developers never thought to test, ransomware delivery paths, and pre-ransomware application flaws. Fuzzing could prevent up to half of data breaches that result from software vulnerabilities, including more than 60% of the vulnerability types currently being exploited in real-world scenarios. And fuzz testing actually did catch critical open SSL vulnerabilities before they reached production, preventing potential remote code execution attacks. So how do we do this with Ranorex, for example? You can do this with other UI frameworks as well, but with Ranorex, it's especially simple. You would create an Excel or a .csv of your inputs with the common fuzz variables such as SQL commands, JavaScript, other types of invalid data for various input types. You would pass the fuzz inputs into your UI fields as variables. I like to name them, fairly clearly. And you can actually see them getting passed into your test right here. And then you just need to add your validations. And this will vary a lot depending on how your application handles errors. There usually will be an error or invalid or disable attribute that you can check for. You can also validate based on the presence of an error element, the error text itself, or both. So depending on if it's just, an error that exists, or if you actually show error text, you can also check for specific SQL syntax. You can test for JavaScript injection by passing in a JavaScript alert and then validating that it's not present. Another very valuable defense against AI-introduced vulnerabilities is end-to-end API testing, which is when you test your full backend flows, including third-party services using live endpoints in a test environment. So this would not involve any mocking at all. So your APIs are basically the gateways connecting LLMs and third-party services to your data. So keep them secure is essential. And unlike unit tests, which only cover single functions or components, end-to-end tests verify the complex interactions between the UI, application logic, external integrations, and data storage, simulating real-world attack scenarios. And this is especially important when taking into account that your application ecosystem is likely tied to several services such as LLM providers, vector databases, and SaaS APIs, all of which are given access to secrets, passwords, and other security-related data. A bug in a third-party service can directly impact your application's security, even if your code is flawless. So end-to-end testing is crucial for validating the security posture of those external integrations, ensuring data integrity and secure communication. So here's an example, end-to-end API flow. So it's a make a purchase. So there's a third-party payment service that could be covered by an end-to-end backend test. This is an example of coded backend API tests done in Mocha Chai, which is a very common coded framework. So you can see here we're going over the happy path. We're doing response validation. We are checking missing required parameter, invalid required parameter. You can do empty request body, missing request body, invalid parameter, missing headers, and no auth, just to make sure that you respond appropriately. And you would assert based off the error code or the status code in the error message. So in Ranorex, what you would do is you would create a user code module and run it in Ranorex. And you would create an action step selected from the library and you could run it. And this can even be in the same project as your fuzz testing because Ranorex is a multi-application software. So basically adding security focused automation to your QA workflow is not only an effective way to broaden your test coverage, but it also contributes a powerful layer of defense to your organization's critical security efforts in the age of AI. But these aren't the only tools you can leverage to keep your application safe. I'm going to hand it off to John to discuss an area of software security you may not have heard of. I hadn't before I met him, DevSecOps.
Thanks, Evan. So before we get into the real in-depth, I just kind of wanted to go over DevSecOps as a concept, an idea, a discipline, because really I think it's more relevant now than ever before. And DevSecOps is really about integrating security into the software development lifecycle. And it's done by coordinating people, process, tooling. And people, we really need to just establish responsible parties within our org. So who's handling incident response? Who's handling disaster recovery? There's certain critical functions that we need dedicated energy behind, but really DevSecOps is not possible without everybody doing their job in their whatever their role is. So we need to write, review, and understand secure code. We need to test secure code. Are we making it a part of our day-to-day and not just test for functional testing, but security testing as well as a part of our role? And we'll get into that a little bit later about why that's relevant. But process is about understanding what are the success criteria for our application security program. What does it mean? What are the KPIs? Do we need to achieve certain compliance requirements? Are we in a heavily regulated industry? Or do we need to adhere to MITRE or the NIST framework, a certain framework? And then from there, we can do risk assessment. So in QE, we deliver our impact analysis. So what is this new feature? What's the impact of this new feature? What is it going to do to our existing customer base? How is changing functionality? Risk assessment, risk analysis is a similar thing. So we need to understand and quantify the risk from a security standpoint. Are we concerned about a nation state attack? Are we concerned about hacktivism, things like that? Does it matter? The answer might be yes. Or are we more concerned about our IP and trade secrets that we want to keep secure, or our customer data? I think that's relevant to all of us, keeping our data secure and doing what we can along that vein. And I often think of it like, well, let's say you're building a warehouse inventory app that exists on a single terminal that's on a air-gapped machine, air-gapped terminal. Well, there's a totally different risk profile than, say, a mobile app that has 100,000 monthly active downloads. So we can take all that into account, and from here we can develop our mitigation strategies. So a lot of that is just conversational. Threat modeling is like, well, what are we actually building? Is it a mobile app? Do we have a desktop component? Can we inventory everything? If we don't have, let's say there's a legacy API that's not accounted for, that might represent the backdoor into our systems that we need to be aware of. And then tooling is what helps us with all this. So we can't, people in process get us a good part of the way there. Just basically discussions with stakeholders like, well, oh great, now our app is agentic. How much do we allow our agents to do? How much permissiveness? How much autonomy? We can build that in as we're building the apps. The tooling comes in because things like, on one hand, we have vulnerability scanners like SAST and SCA, which help us uncover vulnerabilities before we go into production. The flip side of that coin is tools that protect and monitor our apps once we're in production. So we have obfuscation, we have RASP, we have web application firewalls. All this is meant to, once we do our job in QE, in development, Once we get that out in production, we need to have a window into how that's doing and respond and recover if need be, if something does happen. So that's kind of like DevSecOps at a glance, and how we can all be involved in securing our organization and their assets. OWASP, the Open Worldwide Application Security Project, or OWASP, is a not-for-profit organization that provides guidance for creating secure software. Every handful of years, they will publish the OWASP Top 10, which are application security risks. They have OWASP Top 10 for web, mobile, API, because there are different inherent risks in all the different platforms and permutations of software that we create. And within the past 3 to 4 years, they've come out with OWASP Top 10 for LLMs, for agentic apps, and machine learning security. So, if we're, it's a great starting point if we're trying to figure out how to work testing into our strategy. So if we're usually doing functional tests or load testing or performance testing, things of that nature, if we then want to shift, then we could say, okay, well, injection seems to be a critical thing. OWASP has identified that as one of the top 10. How can I work those types of tests into my day-to-day? Okay, and a software security vulnerability is a bug. It's a bug, it's a flaw, or it's a configuration that a bad actor can then exploit to get our software to behave in a way that it's unintended from the original intent, and in some way compromise our confidentiality, integrity, or availability of our systems. So I think there's a tendency to think of a bug as functionality it's not behaving the way as intended, it's not working to spec. That is a bug. And a security vulnerability is like a separate thing. But in actuality, if we don't discover a bug in a QE phase, our customer is going to find it. They're going to report it to support, and it's going to be bad for business. So we do all we can in QE, trying to cover all the bugs that we can, and flesh them out and fix them before we give it to our customers. A security vulnerability is just a bug with just a different sort of consequence. If that security vulnerability makes its way out the door, then that could be turned into an attack, a data breach, data theft, software piracy, IP theft. So it's really the same thing. It's just, it just has a different consequence with different ramifications. So I just want to take a moment to look at a few of the common security vulnerabilities that we should be aware of in our day-to-day. So SQL injection is just malicious code that's injected into an input field to manipulate your application's backend database. And more often than not, SQL injection is used to exfiltrate data. So if we look at this example here, on the left-hand side, that's intended behavior. I want to search for an employee email or employee from this directory. I know the first couple letters of the last name, or the first name or last in this case, and then I find that employee. But if I craft a specially crafted input string on the right-hand side, then I can retrieve the entire database, which is not the original design of this application. Why is this a bad thing? Well, what if they're usernames? What if there's PII? What if there's some sensitive information that was not designed to get out in this context? Well, if I just simply craft a custom SQL statement, then I could get the whole contents of the database. Cross-site scripting, it's another in the category of injection attacks. Cross-site scripting is just a security vulnerability where an attacker injects a malicious script, usually JavaScript, into a trusted website. So in this example, we have a comment section for our website, and we put in our email address and we have a comment. On the right-hand side, again, if we craft a custom JavaScript, then we can get everybody else who comes back to the website to load up this alert message, and I've defaced the website. So this is relatively innocuous, but if you could think about it, in the cross-site scripting attacks that make the news, the script is injected that sends the customer data to a malicious server, or it crafts a SQL an injection script to redirect the users to a fake login page which looks convincing enough that they would log in, and then boom, there are your credentials have been stolen. So cross-site scripting is another big one. File path manipulation. It allows attackers to read, access, write, execute, or modify files or directories outside of the intended web directory. So on our web server, on the left-hand side here, hey, you want to download one of these files. Okay, fine, simple enough. But if you look at the bottom on a hover over, I see that it's being passed through a get parameter. Now, if I take that little bottom string, and I'm sorry, I'm noticing now it's a little bit blurry. That's my bad. But I think you get the idea. If we look at the bottom right, I've then manipulated that get parameter to get the web config. And then boom, I have your full server configuration, and then I can go from there. So what we see here is an example of a download path manipulation, but the same is true for an upload path. If you allow uploading to your server, there's the chance that somebody could upload a malicious file that they could then execute on the server. This is a real thing. It happens. So path manipulation is another. And then finally, insecure data storage. So sensitive information, keys, passwords, API keys, API endpoints, PII, financial data would be stored somewhere where it could be accessible to an unauthorized party. Insecure data storage. So it applies primarily to mobile or edge computing devices, IoT devices, anywhere where there would be some kind of client-side caching of data, shared preferences, SQLite database. Is there encryption on it? Hard-coded credentials. All this kind of stuff could be then reverse engineered. As in this example here, it's just an Android application. I can do an ADB pull, take the Android APK off, APK, the binary from the device, and I can extract it. I can look at the contents, and it's relatively simple to gain access to all this sensitive information. So we think of these vulnerabilities, these software vulnerabilities, we categorize them in terms of CVE and CWE. A CVE is a common, or excuse me, a CWE is a common weakness and enumeration. And these are the descriptions. So injection, SQL injection, buffer overflow. These are descriptions. And the CVE are common vulnerabilities and exposures. And these are publicly available, publicly disclosed flaws in software and even hardware. So to put things in perspective, we talked about 4. There are over 600 categories, such as injection, weak authentication. There's over 600 of these categories. And there are over 300,000 CVEs. It started even a little over 20 years ago. So 300,000 of these things. So this is like, it's really, so what can we do about this? How can we get our head around this? Well, this is where the tooling helps to augment our day-to-day efforts. The tooling helps us. So SAST, or static application security testing, it helps us analyze our source code for these vulnerabilities even before they're compiled. So as we talked about, there's hundreds of thousands of vulnerabilities. It's really unrealistic to think we can just try and manually uncover these, in our day-to-day. We can do a good amount. We can do, give it the college try. We can do a lot, but it's really unrealistic to think that we can think about them and then do it. So, with fuzz testing, automated API testing, these are great techniques to have in your day-to-day. They're great with, injection attacks, buffer overflows. Where SAST helps us is it fills in, because we don't have to craft the malicious payload or to try and take it out. The SAST contains the definitions of all these CWEs. So we don't have to really think about it. We scan our source code, Furthermore, SAST can be done. You don't even need to compile and deploy it. There's no interaction required. You don't have to. You don't even have to have something that compiles. You can just have. You've got 10 lines of code. You can run SAST against it, and you can see if there's any vulnerabilities. Boom! You've generated a bunch of code. You're still working on compiling it. You generated from Copilot or whatever. You can scan it instantly and uncover those vulnerabilities from the SAST engine. Integrates into any existing CI/CD. We can add security gates to our build. So if if you have a branch of code that you're working on, you can pass or fail that build based on criteria defined in SAST. Also prioritize it. It follows the CVSS scoring. So based on risk and likelihood, it automatically provides that for us. So we don't have to think about which one is more severe. We don't have to put the thought into that. It's built in. And then it generates full reports. So if we are doing compliance, we have traceability, audit-ready evidence for compliance, remediation steps, and again, they're all scored so they can help us prioritize based on severity and time to remediate. Software composition analysis. So Devin talked a lot about the third party. Up to 80% of the software we're delivering is third party components. So software composition analysis identifies and manages risks from any open source or third party component in our software supply chain. So things like the Log4Shell, Heartbleed, SolarWinds. These are all incidents that occurred because of a poisoned third party package. It wasn't necessarily anything in our code that we wrote. But again, harkening back to the OWASP top 10, they consistently report supply chain vulnerabilities as being in the top 10. So as we're scanning our code for buffer overflows, SQL injections, things like that, we can also be aware of any disclosed third-party vulnerabilities. And code obfuscation. So kind of the flip side of the coin. We've done everything we can from a testing standpoint to ensure that the code that we're delivering is as secure as possible. We've managed all the risks, but we still have to do things to mitigate that risk once we've gone out to production. Eventually, we have to go out into production. Even if every single day X number of vulnerabilities are reported and disclosed, we still have to go to production at some point. So the flip side of the coin is once our code's out in production, code obfuscation prevents reverse engineering. So the things like the IP, trade secrets, API keys, endpoints, code obfuscation that combats the decompilers, disassemblers, and string table analyzers. So it's key for protecting the code in production. It also, similar to SAST, it integrates directly into our CI/CD. So it can run on demand or it can run as part of our existing pipeline. And it runs on-prem and it can run offline if necessary. So that's code obfuscation. And then RASP is runtime application self-protection. So again, once we're out in production, we oftentimes, especially us, we're building a mobile app, we're building an edge computing device, IoT. We don't have control over the environment in which our product is running, so that could cause issues. So RASP helps us with things with like code integrity and anti-tampering, anti-debugging, root detection. So tools like Magisk and whatnot that are done in a reverse engineering context are very, very important. So these are additional tools that we can add to our toolbox. So just to kind of wrap things up, as Devin talked about quite a bit, as we mentioned, the AI and the agentic workflows, they're subject to hallucinations, misinterpretations, alignment, how's the alignment, bias, all kinds of stuff. So we really need to be vigilant in our day-to-day, keeping human in the loop and sort of overseeing these things. Secondly, the AI generated code has proven to be containing quite a few vulnerabilities. And so that generated code contains security risks. And so then things like security testing, so fuzz testing, API testing, SAST and SCA can prevent many of these issues before we deploy to our customers and our end users. And then finally, defending against reverse engineering and runtime manipulations they're necessary for defense in depth strategies. Okay, so that takes us to Q&A. And okay, so we do have a couple of questions. So first one, do we have recommendations for adding persona and or other context files to AI to help us design and build the tests? I personally don't. Devin, do you have any like in generating the fuzz tests? Do you have any sort of like opinion on this?
I've used AI I've written context files. When it comes to designing and building tests, I mostly have used AI for like making sure that there weren't scenarios I wasn't thinking of and fuzz inputs I hadn't thought of. So in that sense, I would use it. But yeah, for persona, I've done that a few times too. So you can say like, act as a cybersecurity expert and this is my type of application, like what types of penetration attempts can I make? Or, it might be able to help you with like finding your most likely cause of vulnerabilities. I find I have the biggest, when I create context files, I always tell it to give me like three different options and then give me the pros and cons of each, or to create a solution for me, but then grade it. Or I'll have it create a solution and I'll be like, okay, what types of vulnerabilities would this not catch? So yeah, because the AI is not going to check itself unless you tell it to. So I would just, if I were making context files or personas, the persona, I would definitely say something like, I know, either an elite hacker or cybersecurity expert or something. And then for the context, I would build in multiple options. I would build in decision checkpoints. I would build in the agent critiquing itself or trying to come up with edge cases itself. And I would also build in tests, and then obviously outlining your business rules. And you can even put in prompts to be like, warn me if I'm about to, if any of these paths could lead to a security vulnerability. But the biggest thing would be I wouldn't let anything pass that I hadn't reviewed personally. So,
Yeah, so regarding RASP, do we consider a user's browser a potentially compromised environment? Yes. We think about browsers, there's different things to consider when the source code is living in the user's environment. So if it's running on desktop, the full source code or a good majority of the source code is actually living in the end user's desktop. And the same with a mobile application. So when I build an APK and deploy it through the Play Store, I have all the logic. So in some way, shape, or form, API keys, uh, tokens, things like that could be cached inside the APK itself. So that's where the real issue exists. But still, there are still things like dev tools where you can access certain information. You might be able to reverse engineer to a certain extent. So yeah, I mean, I guess not totally, but somewhat. So we do have RASP checks that are designed for the browser itself. So we do DevTools blocking. So is there really any reason for somebody to be examining the DevTools once they get to your website? Maybe. But once you pop over to those DevTools, you're going to see all the API communications and you can look at all the source. So whatever exists in JavaScript, TypeScript, um, So yeah, I mean, I would say yes. So the runtime checks do exist for browser as well. I think DevTools blocking, the tamper detection as well, domain locking, date locking. So if somebody does take the JavaScript from your website, try and copy it and run it in their context, is it running under the same rule? No, then we should block that. That's not something we should allow. Also, debuggers. You can debug within the browser. You don't necessarily need your customers to be doing that. Um, so yeah, hopefully that answered that. The next question is a Ranorex question. So
Yeah. So with Ranorex, I mean, it's kind of Ranorex can do UI-based automation, and obviously doing form validation, making sure that you can't inject SQL into an input field or a JavaScript instruction into an input field. Anything that someone could get at through the front end of your application, you can test via a front end testing framework like Ranorex. And Ranorex also, you can write your own user code, which basically means you can write API tests as well. And with that, you basically would just have to think like an attacker would. I would usually prioritize security based on the most likely and the most frequent vulnerability points, which are usually going to be prompt injection. And a lot of people don't check their auth on APIs. I worked for a company where you could just save a session cookie from someone logging in and you could just use that cookie and over again. We actually used that in our tests just to get past login. And nobody really paid attention until the QA engineering manager got into one of our test environments and changed every single picture in our application to a unicorn. That's when they took it seriously. So I would say Ranorex, any kind of testing that you can do, through just a basic end-to-end API test or like front-end automation test, you can do that with Ranorex. You would just have to use, um, you know, uh, attack inputs instead of regular inputs. And then for the API test, you would try, like, can I get around this auth? Can I, put a SQL injection or JavaScript into like a request body? And, and then the security scanning things kind of cover the rest, basically.
All right, team. I think we're wrapping up on time. What we can probably do is get the answer emailed in our
Okay.
follow-up email. And we might just wrap it up for today. So thank you, John. Thank you, Devin, for this session today. It was really insightful, and thank you everyone for joining. Keep an eye on your inbox for this recording and potentially some answers that we're waiting on. And have a great Tuesday. See you later.